Okay, good afternoon, everyone. We're going to go ahead and get started. I am Amber Mace. I am the Executive Director of the California Council on Science and Technology, and we are thrilled to have you join us for this first virtual briefing. Before we get started, I'd like to acknowledge that this briefing was originally scheduled a couple weeks ago. We decided to reschedule it to honor the shutdown STEM movement, asking those in academia and STEM fields to stop business as usual in order to develop an action plan to work against institutional racism in the STEM communities. Affirming that Black Lives Matter and supporting the Black members of our CCST community is an essential priority for us. And we are in ongoing conversations, doing a lot of learning, a lot of listening with our team and our CCST Science Fellows to identify ways to institutionalize a lens of equity in everything we do, an effort we are committed to. We'll have more to say on this as we develop our plan of action and our accountability for implementing this plan over the long term. And for now, we are grateful for your flexibility and that you are here today to join us. Let me tell you a little bit about CCST as an organization. We were created at the request of the California legislature to serve as an entity to bring in expertise from a whole network of experts across our university and research partners throughout California. California is so lucky to have such an incredible network of academic and research institutions and universities. And our mission is to make California's policies stronger with science. We do this by partnering with our universities and understanding the needs of decision makers, and then bringing to decision makers what we hope for is actionable, timely, useful, science-based information to inform the work that they do. We do this through big peer-reviewed reports. And for example, we did one recently on underground natural gas storage, and our moderator here today, Rob Jackson, was one of the steering committee members participating in that study. So we're grateful for his participation on that. We also have a Science Fellows program where we bring PhD scientists and engineers from across the country who want to learn how policy works and bring their science expertise to bear directly to the decision-making process in the legislature and in the executive branch. And I am hoping we have a number of our Science Fellow alums and Science Fellows on the webinar today. We do briefings like this. This is a fantastic way for us to connect our experts from our network directly with decision makers to create a conversation that we hope will just be the beginning of a conversation and one that we anticipate will continue. So this briefing today is part of our series on decarbonizing California. And you can find more information and a video from our previous briefings on our website, and you can see some of the other topics that we've covered. So now I would like to introduce Dr. Rob Jackson. He's a professor of Earth System Science at Stanford University. He is a senior fellow at both the Woods Institute for the Environment and the Precourt Institute for Energy. He's an expert in the impacts of climate change and drought on forests and grasslands. He chairs the Global Carbon Project, which works to measure and reduce greenhouse gas emissions. And as I already mentioned, he previously served on the steering committee for one of our big peer-reviewed reports on underground natural gas storage. So quite an expert. We're so grateful to you, Rob, and to the whole panel for joining us for this conversation today. Take it away.
Well, thank you, Amber, and thank you all for attending. We're grateful for CCST for putting this on, and also for their flexibility in really, I think, making the right decision to delay a couple of weeks ago. So thank you on both counts. Well, we're here today to talk about natural pathways for carbon sequestration, and they've received considerable attention recently, and justifiably so. So the Trillion Trees initiative is gaining steam. Programs such as the Bond Challenge aim to restore hundreds of millions of acres of degraded forests around the world. And that's important because deforestation, for example, still contributes about 1/6 of global carbon emissions. And soils, as we'll talk about today too, are increasingly seen as win-win opportunities to sequester carbon while also reducing erosion and improving water holding capacity and nutrient retention and things like that. Here in California, we have some of the country's most ambitious greenhouse gas targets. SB 100 mandates carbon neutral retail electricity by 2045. SB 32 requires us to reduce greenhouse gas emissions 40% by 2030, just a decade from now, compared to 1990, an extremely ambitious target, and then 80% by 2050. So natural pathways and working lands have to be part of that solution. We basically need every arrow that we have in our quiver. And it's important to note that the state views this mandate broadly. So it's not just forests and farmlands, but also rangelands, urban systems, wetlands. So all of these are fair game for our discussion today. And against this backdrop, we have to consider other challenges and factors. Record wildfire seasons in recent years suggest that in places, we may need to remove biomass rather than add biomass to a landscape. So how do we balance such trade-offs? Should the state consider producing more biomass energy based on fire prevention efforts? Will increasingly severe droughts make ecosystems more vulnerable to losing carbon currently in place? And what management strategies can we apply differently to store carbon and reduce risk? So if we want more trees, should we let them regenerate naturally or plant commercial varieties that might be more resilient in a warmer climate 10, 20, or 50 years from now? So what are our options for rangelands and other systems? Well, this is the context for our webinar today. I'm grateful for our audience. We've got a terrific turnout, and we're fortunate to have 3 experts to discuss these issues. Patty Oikawa from Cal State East Bay, Asmeret Berhe from UC Merced, and Matthew Potts from UC Berkeley. And here's our format. We'll begin by having the panelists introduce themselves and answer an opening question. We'll then have about 10 additional minutes of questions and discussion amongst the panel, but we'll quickly open the session to your questions. We got some great ones from your RSVP comments, so we have those queued up, but there'll be plenty of opportunities to get to your thoughts. There's a lot of expertise in the audience from universities, agencies, NGOs, different groups, national labs. All right, so here's the question we're going to start off with. I'll begin with Patty. And Patty, what are the greatest opportunities in your respective system for carbon sequestration, both in total size and relatively low cost? So please introduce yourself and take a crack at that first question.
Okay, great. Yeah, thank you for introducing us, Rob. So I'm Patty Oikawa again. I'm a biogeochemist, and I specialize in trace gas measurements, particularly greenhouse gases, so carbon dioxide and methane. And I typically take these measurements at the ecosystem scale and use the data to help build process-based biogeochemical models to help us estimate greenhouse gas budgets from natural ecosystems, particularly wetlands, agricultural lands, rangelands. And so I've been working in those systems in California for about 7 years now. And I also co-authored a greenhouse gas offset protocol for wetland restoration in the San Francisco Bay Delta region. And then I've also joined a group of scientists who are being funded by the Strategic Growth Council right now to look at soil amendments, particularly compost amendments to rangelands, and also rock amendments, biochar to agricultural lands, and kind of experimenting with these types of soil amendments across California to see how they can enhance soil carbon sequestration. So that's kind of my brief introduction. Going to Rob's question. So I guess I'll start with wetlands. So there's a lot of opportunity for carbon storage in wetland ecosystems. So of course, these are flooded systems. There's not a lot of oxygen in the soil. And so carbon that gets deposited there can be maintained in the soils and stored at really high densities for long time scales, so thousands of years. And so we have great wetland restoration opportunities in California. For example, in San Francisco Bay, we are, the Bay Delta region has lost about 500,000 acres of wetlands. And there's obvious potential just in the Bay Delta to restore some of these areas, and thousands of acres are actively under restoration at the moment. So there's a lot of effort being done in that area, and I think it is scalable. There's a lot of potential there. Wetlands can sequester, depending on the type of wetland, you're talking about anywhere from 1 to 6 metric tons of CO2 equivalents per acre per year. So that's kind of similar to taking one car off of the road. And so when you're talking about hundreds and thousands of acres of wetland restoration, you're starting to get to numbers that are more significant. They also have incredible co-benefits. I'm happy to talk about that more later. But the other big, I think, potential is for soil amendments to places like agricultural lands and rangelands, and that's quite a bit more scalable. So, 40% of the land surface in California is rangeland. And we estimate that even if you applied compost to half of that amount, you could be sequestering around 30 million metric tons of CO2 equivalents per year. And so that is, again, much more scalable. There's a lot more land surface to potentially work with in those types of environments. But I think I'll answer more questions about that later.
Terrific, thanks.
Yeah.
Asmeret?
Muted.
So you're muted.
Sorry about that. It would have helped if I unmuted myself. So as Rob mentioned, I'm a professor of soil biogeochemistry at the Department of Life and Environmental Sciences at UC Merced. So my background is in soil science. I'm trained and especially focus a lot of the research in my lab on questions dealing with biogeochemical cycles of carbon, nitrogen, and phosphorus, especially in the soil system. And in my lab, we really emphasize on thinking about the mechanisms that allow carbon to stay in soil for hundreds and thousands of years, instead of being processed with the decomposition and immediately going back up into the atmosphere in the form of greenhouse gases. And so this means we spend a lot of time thinking about different types of carbon, different forms of carbon stored in soil through different associations with reactive minerals in soil that facilitate the long-term sequestration. And specifically, we also spend a lot of time thinking about soil systems that experience physical perturbation or physical change in the system that occur through things like erosion, fire, or change in climate that would bring about shifts in temperature or even shifts in water flow through the soil, and how those would affect not just the amount of greenhouse gases that are released from soil, but also the mechanisms that control how and for how long carbon can be stored in soil. So our field of study then covers a lot of these process level questions and mechanisms. But then on the other side, we spend a lot of time thinking about sustainability of soil, and in particular questions about land degradation. So for those who might not be aware, somewhere between a third and half of all soils around the world, including a lot in California, are considered degraded, meaning their potential to actually support plant productivity is seriously compromised because of degradation that has occurred by human actions. And typically this is a result of excessive deforestation, more conventional agricultural systems, and application of excessive amounts of agricultural chemicals also in these systems that have caused considerable drop in the health of the soil, which in many ways is translated into drop in the amount of carbon that's actually stored in soil. So when we think about soils and climate change, then a lot of the work that we do thinks about how can we bring back some of this carbon that was lost from soil by human activities. So for reference, there was a fairly recent study that indicated that we've lost somewhere on the order of about 130 to 140 billion metric tons of carbon into the atmosphere just from agricultural practices that have considerably degraded soils. So we're talking about a lot of carbon that has been released from soil. So we think about how can we put back some of this carbon into the soil through sequestration mechanisms, addition of carbon even from compost on biochar. One of the active research that we're conducting at UC Merced right now is funded by the California Growth Council to actually look into specifically these questions of how we can use a lot of the excess biomass and manure that we have in California as an input to soil to build up soil carbon, but also reduce fluxes of greenhouse gases, in particular nitrous oxide and methane from soil. So in addition to that, as you might see in my record, we've also spent time thinking about the role of soils in human security in the 21st century. And this is a very large overarching issue that touches upon soil health and soil carbon sequestration as part of the measure of soil health, but also even thinking bigger about how soil in general controls the security, not just water security or food security, nutritional security. We're now talking about even geopolitical security of human communities in the 21st century that I'm happy to answer questions about afterwards.
Okay, great. Thank you. Matthew, you're up.
Yes, I'm Matthew Potts. I'm a professor of environmental science at UC Berkeley and also affiliated with the Blum Center for Developing Economies. My work really focuses on land use, planning and land use policy. Much of my early career I spent in Southeast Asia thinking about tropical forests, thinking about how you mainstream sort of biodiversity considerations into production forests. That expanded to looking at plantation agriculture, oil palm, cacao, and coming to California about a dozen years ago, sort of really got, ingrained into issues in the West. And sort of the past couple of years I've been sort of thinking about how do you, bring synergies in across multiple ecosystem services. When we think about climate, we think about fire risk reduction, we think about, public health effects, we think about, changes in risk to property. So a good, representation of that has been my work with the Lake Tahoe West Restoration Partnership, which really sort of started looking at, around Lake Tahoe, what are the paths we can take to build forest health and forest resilience, and what are the trade-offs we face. So my lab really right now is thinking about and sort of focusing on this concept I like to call co-production, sort of thinking about human systems and how natural systems interact to produce ecosystem services or disservices. And sort of to move on to Rob's question and sort of thinking about where the opportunities lie, there's a substantial amount of opportunities that lie in the forest sector, whether it's changing forest management practices, which are going to be synergistic or maybe not so synergistic with fire risk reduction, which Rob alluded to, drought and climate change. And the other area I think that has high potential is reforestation. If we think about areas that, sort of high severity fires like the Moonlight Fire, that's a lot of areas that aren't going to naturally regenerate. So assisted regeneration planting will actually bring those forests back. So I'm going to pause there so we can dive into more questions.
Okay, thanks. Let's take we'll do a couple of questions and quickly go to audience. But let's go back to Patty and Asmeret together. You both talked about soils a little bit, and maybe if you talk about some of the co-benefits for soil storage. But I'd also like to talk about the practicalities of this. I mean, Patty, you mentioned the millions of acres of rangelands that are out there that could be manured and or composted for increased carbon. I mean, how would we do that practically? I mean, is it cost effective? Are you talking about driving tractors over rangelands? Are you talking about some kind of biochar seeding from plains? I mean, and one of the challenges of these natural solutions is ways to do it that are cost effective and that compete with other things. So maybe for both of you, what are some co-benefits, particularly from soils, and how do we do it in places that aren't farmland, where people are traveling over them regularly?
Well, Asmeret, I can talk first really quickly, but so for compost amendments to rangeland, I mean, agricultural fields, it's a lot easier to access. So that is one of the issues with rangelands is, getting the actual compost to the rangelands spread over the surface. So it will take some logistics. And ideally, of course, you'd be removing and using compost and manure that's produced locally and nearby. And so a lot of the experiments that have been done have been in places like coastal prairie grasslands where there's a lot of manure and compost being produced locally, and it's a little easier to access. But there's also really great greenhouse gas benefits when you're taking these organic materials out of places like landfills, places like manure storage facilities that are creating a lot of methane. And so reducing that load and taking some of that load off of them, even if it is a little more logistically complicated, there's a lot of greenhouse gas benefits there. And of course, all of these approaches are going to take money. So there's definitely cost involved with this. I also just wanted to mention that there's potential enhanced, drought resilience for these amendments to grasslands. So, when we're talking about climate change and fire regimes and things like that, this could help play a role in that as well. And then when you're adding amendments to soils in like agricultural settings, you can have, decreased use of other types of synthetic fertilizers and increased productivity of these agricultural systems because of these amendments. So there's positives and economic incentives in that front too.
Yeah, that's great. Thank you. Maybe Asmeret, you could follow up that, thinking about the co-benefits of soils, but also, some of the practicalities. We had a couple of questions in the RSVP responses. Lawrence Ford asked about carbon sequestration in rangelands. And then Greg Hayes from Cal Poly, talked about, are there concerns of sequestering carbon in rangelands with the conservation of species that require poor soils, for example? So some of the unforeseen consequences that could arise from these practices. So, where are the synergies and what are some of the trade-offs or potential risks?
Yeah, so as I mentioned earlier, to answer the last question first, if I may, a lot of the work that myself and other people have been doing is really to restore the habitats to their native states pre-disturbance. So I feel like in that case, the disruption to sensitive species that he mentioned in that last question might not necessarily be a huge concern considering other things. But I agree with Patty in how she described, the real costs that, kind of landowners have and managers have to incur to implement conservation practices, climate smart land management practices in general, including for applications of compost and biochar. So with that understanding, actually, our project that I mentioned that was funded by the California Growth Council is aiming, and we're actually working on it and testing prototypes right now, is to figure out a way where we can help farmers reduce some of these costs by producing the biochar, for example, locally using mobile units, instead of requiring large pyrolysis, systems and units somewhere else where they have to transport their excess biomass to have it charred, bring it back, and pay the cost for the pyrolysis too. So having a mobile system like this seems like more of a cost-effective. It makes sense for small-scale landowners in particular, but it's still recognized that there's cost to doing so. What would be helpful from the way I think about it is to take a slightly larger perspective here, right? So in places like California, we're in one of these systems where it actually makes sense to think about how we're going to use a lot of the excess biomass that we have from agriculture and forestry and manure waste to figure out a way we can deal with this waste. We need to figure out a way to deal with these wastes anyway, right? So figuring out ways where we can apply them to soil to restore soil health and contribute to carbon sequestration is a win-win all around. So it might obviously not be a cheap endeavor for a small scale landholder or manager, but if we think at a larger scale where we're actually reducing fluxes of methane, nitrous oxide, ammonia, reducing the public health cost from all of this waste that could potentially enter our water streams, for example, then we can start seeing that there is a realistic path for how we can subsidize perhaps some of these practices to make them more cost effective and realistic for farmers and landowners.
Great, thanks. For the audience, we've got 110 of you out there, which is fantastic. It's time to submit your questions. You can go ahead and do that through the Q&A, which is found at the bottom, the button at the bottom of your screen, if you're not familiar with Zoom, which probably everyone is by this point in the shutdown. So go ahead and submit your questions and we'll start collating them. Matthew, let's come back to forests, if I may. And forests definitely provide some of the largest opportunities for sequestration in California. Obviously we want to maintain forests that we have, We have opportunities for restoring forests. Yet we also have an active forestry industry that's important for our economy. So what are your thoughts on the best opportunities within forestry? And I would include management for those. Maybe some comments about, genotype planting, thinking about a changing climate in the future. So give us some more thoughts on forestry in particular, both sequestration, but also perhaps management.
Yeah, so I think there's some real opportunities there and some real synergies that sort of go with the cost structure too. So if you look at sort of what are the lowest cost solutions, sort of going to getting to neutral, really, taking those numbers, which are good numbers, sort of saying at an average cost of $8 per ton of carbon, you can get up to 15.5 million tons by 2045 from just changes to forest management. And that gets to some real synergies that are out there in the sense of, we know we have overstocked forests, we have a century of fire suppression, we have a changing climate, we have increased risk. And so going in there and reducing that risk, storing that carbon in the larger, more durable trees that are more fire resistant, but also reducing the risk of high severity fires is a win on that side. And then the question, which we've already sort of discussed, is what do we do with all this residue? And so there's where other opportunities really exist in sort of taking that residue out. California has a complex topography. Population centers are not necessarily where forest residues are. We don't have the mill capacity. We don't have the infrastructure that we once had. But given that as a society, we're willing to pay to reduce fire risk for public health, there's an opportunity to invest that into new infrastructure to, either whether to utilize it in traditional ways, creating biomass to electricity, or thinking of maybe of advanced biofuels, or harvested, turning some of this wood product, smaller dimensional lumber, into cross-laminated wood timbers that you could put into buildings that may, would even have an additional substitution effect out of using concrete to build large buildings. So there's real opportunities there. And I think Rob is right. The other half of it is, as we think about restoring, we have to think about what we want to restore and how we want to restore it. And how do we think about a future climate versus a current climate in terms of what these trees or what these grasslands will be living in.
Great. So let me follow up with an audience question. This one came in from Austin Kerr for you again. And is the carbon stock of an existing forest in the Sierra relevant if the forest isn't ecologically stable or would not be resilient to wildfire?
I think that's a very good question. I would tend to say we don't really have a very stable carbon stock as it stands now. And so that is why we need to move forward with increasing the pace and scale of management actions to reduce fire risk. And then the question begins, how do you transition and choose to do that? And there's opportunities in whether you use more, bringing fire onto the landscape. We know California fire return intervals pre-1870, pre-1850 were 15 to 20 years. It looks like it's every 100 years. Or we go into using more mechanical processes where we reduce the biomass. And we could still go to piling and burning, or we could begin to move that biomass out. So I think we know we have a lot of carbon there. We now know it's not very stable, whether it be droughts and fires. And there's a real opportunity in the short run to decide how we want to stabilize that pool and reduce the risk of large catastrophic fires. Fires are reality and they can be built into the baseline. We just don't want to have that baseline shift too much.
Okay, good. Maybe as we go to more audience questions, let's take one more sort of broader question, again, sort of thinking about the practicalities of how we would do this. And it's also related to a question that Mike Warren submitted, CalGEM, through the RSVPs. But so how can natural carbon be measured and verified? I think the issues are different for a forest, where you might use satellites versus soils. What are the transaction costs? At what scale could we verify soil sequestration? Is it at the plot scale or more at the practice level? So maybe a few thoughts from a couple of panelists on the practicalities of and the costs of verification and monitoring. So how would we go about doing this?
I know, I know for wetland work, we are working right now on a more accessible modeling tool. So models for these greenhouse gas budgets for wetlands are getting better and better, and we're trying to right now make them more accessible and usable online through platforms like Google Earth Engine, which uses, like Rob was saying, satellite imagery to help support our understanding of the plant canopy and how much photosynthesis is actually occurring. And then we can also use these models to help us with constraining budgets of methane coming out of these ecosystems, which is another important factor to account for. But I would say for wetlands and agricultural systems, especially when you're talking about large scale implementation, that modeling and using satellite support, soil maps, and can be really helpful for that scalability question.
So unlike forests that you could see above ground and you can quantify using, relatively speaking, easier remote observation tools, soils are obviously harder partly because we don't necessarily have highly reliable and easily accessible remote sensing tools to measure soil carbon and change in soil carbon due to different practices at this point. But the technology is moving, I think, at a breakneck speed, if I may say that. So there's a lot of efforts out there to develop technology that would allow us to verify things relatively cheaply without having to sample over and over again across, difficult terrain, for example, or different types of biomes and things like that. As Patty indicated, there's now fairly well-developed models that could help us extrapolate to large areas from known areas that we can monitor repeatedly, perhaps, across topographic gradients, across biomes, as I said. And we're also getting very good with using big data approaches to compile a lot of the data that's out there where people have measured carbon and its change as a function of many different variables to allow us to develop then reliable metrics and relationships through which we can realistically estimate what the effect of one practice or change in practice could be versus another. So I think it's a combination of approaches. The most straightforward approach is to dig a core and characterize how much carbon's there, but that's not always possible or even realistic in large scale areas that we're trying to monitor. So typically folks these days supplement it with modeling and other remote sensing approaches that can help us explain relationships.
Okay. And while we're on the subject of soils, before I go back to Matthew, here's an interesting question from anonymous submission. Is there a risk of pathogen transmission when transporting compost from one part of the state to another to use as an amendment?
I can start if you want. So generally speaking, it's a risk, right? Pathogens is a risk that's potentially part of applying compost. But this is also part of why compost is treated at high temperature for long periods of time to presumably take care of, in particular, any living things, pathogens that could cause disease. I recognize, and I think it's a major area that's recognized by anybody who works in compost, that even more than the risk of pathogens, there's that ick factor, right? Where people are really not comfortable compost being used in foods that they eat, especially ones that are not cooked, i.e. fruits and nuts and things like that, potentially. And so I think this is an active area of research that multiple folks are trying to address to more than anything, I think, to recognize and to give information to the public on where are the risk factors and where are things we don't necessarily have to worry about with pathogens being transported or even applied to soils too early without worrying about risk. And there's continuous monitoring also to make sure that compost treated soils, if they're being used for, I mean, in many cases, they're not even being used for plants that human beings are eating, right? This is why there's a lot of effort with compost-related research in rangelands right now, is to minimize the risk exposure to human communities. But we've seen, I think, from rangelands that the risk is not necessarily huge as long as the compost is treated very well, and it could be tested ahead of time before being transported or applied to soil too.
Okay. Matthew, let's go back to you on verification and measurement and such. So what are the options for forests and how can it be done effectively and cheaply?
Yeah, so I mean, I think there are, if we're thinking about California, thinking about the US, we do have the advantage that we do have, good ground data, forest inventory analysis plots put in by the Forest Service. You know, they have their pluses and minuses. We also have, you know, the great potential of remote sensing. So I think the real future there lies in sort of synergizing those two. And I feel very confident in those and sort of getting at issues around, you know, stock, or really around changes in detection and cover, where I think I always have concerns, and it goes into just sort of the uncertainty about thinking towards the future, is, you know, the use of models to sort of project future conditions in forests, and how will we think through those carefully. I mean, I think one, you know, core issue that we might say exists, we know exists in sort of using the FIA data, is it can be linked to the forest vegetation simulator, another Forest Service tool, but it's the need to sort of really parameterize that data and sort of use the repeated inventories to build more accurate models. And that doesn't even get into the larger sets of uncertainties that come in with climate change and drought or the fire risk. So I think the opportunities there, we're going to get really good at monitoring and verifying, but I think we're going to still face some uncertainties on how we project into the future and how we bound those uncertainties when we think about these negative solutions are very important.
Okay, thanks. We had a question from Gary Link, Ducks Unlimited. Thoughts on the value wetlands play in carbon sequestration, as well as ancillary benefits that wetlands provide. Patty, you touched on this a bit in your opening statement, but could you expand on that a little bit and provide us a bit more information and detail?
Yeah, I mean, I think, you know, as I mentioned before, I think wetlands can play a role. I wouldn't say it's going to be a dominant role in these. I mean, forests and rangelands are obviously a little bit of the more heavy hitters in this sense, but they provide really incredible co-benefits. So they occupy a small landmass, but they do help with sea level rise and preventing flood risk. They provide incredible water quality, so reducing nitrogen runoff, providing habitat for endangered species and migrating birds, and also really great public access. I know there's in the East Bay, for example, we have one of the largest wetland restoration projects in the US, and it's right adjacent to disadvantaged communities. So it's providing great green space areas to go biking, bird watching, those types of things. So it offers all these incredible co-benefits for us in the Bay Delta, and, you know, places where you're going to be grappling with sea level rise. But I would say that, you know, originally in California, we had about 30 million acres of wetlands, and we've lost about 90% of those. So there is still a lot of potential for restoration of these systems. And I would emphasize mostly working with, you know, the tidally influenced wetlands that have some of the higher salinity regimes, which really takes methane out of the equation. And so the carbon impacts are very, very positive, very, very well demonstrated. The carbon sequestered, again, for thousands of years. So I think it's a really great tool for us.
Okay. Let's think a little bit about land ownership and management now. Maybe I'll go to you, Matthew, first. Thinking about, we have forests that are public lands that are federally owned. We have private forestry, private lands across the state. We have tribal lands. I think, Patty, you've done some work down in San Diego and in certain places. You know, so maybe starting with you on forestry, Matthew, you know, what are the differences? What are the challenges in dealing with public lands versus private lands? And the incentives are clearly different. The options are different. So how do we think about land ownership in this matrix of opportunity?
Yeah, I mean, so I think one thing is obviously the federal government is the major owner of lands in California. So in some sense, thinking about how we move forward, it'll be thinking about how we work with the federal government to move forward and sort of improving management on these lands. Many of these lands haven't been managed for decades. And so how do we develop good neighbor policies, how we engage in them in active planning that sort of leads to, you know, fewest forest conditions that balance a wealth of goods and services from forests. Turning to sort of privately owned land, that land is obviously managed probably more primarily for economic incentives. So in some sense, it probably has a lower fire risk. It's probably, you know, more growing faster, but there's more harvesting. So that requires conversations on how we view harvested wood products in terms of what's happening to them. How do we want to count carbon, whether we want to count in forest carbon or the whole including the wood product system. So the challenges are different. How do we think about endangered species biodiversity? So I think there are many stakeholders at the table when we think about state or federal lands and balancing those trade-offs and coming up with a socially acceptable contract on how to move forward. Managing those lands always makes it complex. On private lands, we just want to think about how we want to regulate or incentivize certain types of behaviors that are consistent with the public good.
Okay. Thoughts from you, Patty, on the same question?
Yeah, I mean, you mentioned I think there's a lot of great potential collaborative relationships with tribal lands. And so the group that I'm working with that's funded by the Strategic Growth Council has an active collaboration working with the tribe down in San Diego and the Intertribal Agricultural Council, and trying to kind of work with those groups and learn from them and the practices that they're using on their lands that are really great for soil health and soil carbon sequestration, learning from those practices and sharing our data and working on implementation on those lands, and trying to get people involved with the carbon markets too. It can provide a financial incentive for more sustainable land management. Yeah.
Okay. Any thoughts from you, Asmeret?
Yeah, I think in general, I think I agree with both what Matthew and Patty said. For land management in general, that is private, some public, tribal, and different arrangements, right? At some level, it has to do with society's willingness to pay for restoring the ecosystem and for the health of the ecosystem that we all benefit from. And so if that's the case, then we have to kind of think in a larger scale about the social contract between the state, the land managers, and all the users and people who benefit from these lands. I think one example that relates to this in some way is what we talked about earlier about costs of composting and other land approaches for restoring degraded land and for promoting carbon sequestration, right? They may very well be very expensive for the individual landowner to do, but if we all agree that carbon sequestration in these lands is for our collective benefit, then we can figure out mechanisms where we are helping address some of those economic challenges that landowners could face to restore their land and contribute to carbon sequestration that we all ultimately benefit from. So in many ways, I think these are very well aligned issues, regardless of what ecosystem you're talking about.
Maybe we could stick with you and follow up. We had questions about interactions of soils and water quality. We have issues with nitrates, in some places phosphates in groundwater. What are the opportunities for remediating or reducing some of those issues? And are there cases where our practices could worsen them?
Yeah, so a big part of the current, in particular nitrate, but also phosphate problems that we're dealing with, meaning enriched nitrate and phosphorus concentrations in surface and groundwater systems in the Central Valley, for example, has to do with agriculture and excess application of agricultural chemicals, as well as animal waste into our soils where we're using for cultivation, right? And because these soils are so degraded at this point, compared to where they started from when they were, kind of had wetlands and where more carbon-rich soils historically, when we adopted, when communities in California early on adapted intensive cultivation systems, the soils got degraded, they lost a lot of carbon, and their ability to retain water nutrients was considerably compromised. And so now when we have these large production systems where we're applying excess nitrogen and phosphorus, the soils don't have much capability to hold on to it. So a lot of this nitrate and phosphate immediately leaches out the soil at the bottom of the profile and kind of goes into our water systems. And that's a huge health crisis in the Central Valley and beyond, right? And one of the major things we have to do to address this concern, which is, in so many cases, and the work in my lab and labs of collaborators at UC Merced have tried to address these issues together, because issues of carbon sequestration, reducing greenhouse gases from soil, and issues of reducing leaching of nitrate and phosphate from soils are very much related. So if you can increase the health of the soil and its carbon content, and you're facilitating aggregation in soil, you promote better ability in these soils to actually hold on to water and nutrients for longer. So that means this is nitrate and phosphate that's not entering our waterways. For example, we had a demonstration project where we applied biochar as well as biochar that we tried to enrich with nitrogen and phosphorus from these dairies that have a lot of excess waste in terms of nitrogen and phosphorus. And in both cases, in both scenarios with just plain biochar as well as biochar enriched with the manure, we noticed considerably higher potential of soils to hold on to nitrogen, phosphorus, but also at the same time reduce greenhouse gas fluxes, including for CO2 and nitrous oxide. So the benefits are interrelated, this is why I think, personally speaking, I believe one of the best things we could do for climate mitigation when it comes to managing natural ecosystems is address issues of these highly degraded soils, in particular soils that are in agricultural systems right now that continue to be degraded, because those systems also offer considerable potential for mitigation, climate mitigation, I mean, to the tune of something like close to 1 petagrams of CO2 equivalent per year, and with a potential adoption across 100 million hectares globally. And this is not even considering, changing grazing land management practices or cropland management practices, or even changing the type of plants we're using or biochar application. So there's a considerable potential here for us to address two of these major environmental problems of our time by just tending to soil health.
All right, fantastic. Gosh, so much to cover, so little time. Here's an anonymous question, which I really like. When modeling benefits, disbenefits, and co-benefits from management plans, are there key data sets that California should be focusing on and collecting? So, what are the data sets that are key to implementing some of these? And I guess a parallel question that's also came in is, in what ways has California led in managed lands, and in what ways have we lagged what other states have done? So what are the opportunities that we have undertaken and also missed compared to other states? So let's start with data sets and then think about the the comparison to other states as well, and you can tackle them together if you like. Matthew or Patty?
So I would say, well, right now for the amendments research, right now what we're exploring with our Strategic Growth Council grant is looking at sort of combinations of amendments, which I feel like is something that hasn't been explored very much. I mean, Asmeret was just talking about manure enriched biochar and sort of bringing some of these things together and creating synergies potentially. I think that's an area. I mentioned like rock amendments. We're using things like gypsum in combination with compost. I think there are a little more experimentation and data sets needed in that area. I think for wetlands, California has had really great, is providing great continuous data sets on methane emissions from wetland ecosystems. We have some of the best continuous data records of that in the United States. So I'd say we're doing well on that front, but there still could be more. And I think bringing all of that together into models and being able to do ecological forecasting and biogeochemical forecasting into the future is something we need to work on for sure.
Okay. I mean, Matthew, what about forest and other ecosystems? Are there satellite-based data sets that we should be using more fully, LiDAR for canopy height and such? Are there bottom-up data collection exercises that we might need? So what are the data sets that we should be focusing on? And then also, are there other things that other states have done that we haven't yet that we should be doing?
I think we face a different challenge than large parts of the U.S. in the sense of we have a lot of publicly owned land, as opposed to if we think about the Eastern U.S. and we think about forests and who owns forests. So in some sense, the challenge we face is a little bit different there. I would say from a thought leadership, standpoint, California has been very good. We have registered professional foresters. We have very strict standards. We have very, maybe, depending on who you talk to, cumbersome or very, good forest management practices or planning practices or requirements. I think where we've maybe not led quite as well, and I would maybe look to Canada or other places, a different, forest system, is in the sense that we have lots of models out there that have been developed by different agencies and different groups. We haven't really worked as a group to really harmonize and sort of decide on a set of models to model going forward if we think about working lands. And the other part is, I think, when it's natural in forests, you walk around and you see the trees, and we're very good at counting trees, measuring trees, alama trees, figuring out how much above ground biomass it is. It's sort of, how do we think about these other pools, the woody debris, the soils, and sort of how are all these pools linked, and how can we get to some, reduce the error and get a little bit more precision on what we're estimating in those pools and the feedbacks between them. Because I think until we gain that full understanding, I'm just thinking of a paper that came out yesterday looking at reforestation in China that showed some differences in sort of soil organic carbon changes after reforestation, depending on the initial stock of the soil carbon in there. It might be intuitive to our other two panelists, but in that sense, there's the need to really sort of get at those pools a little bit better.
Yeah, some interesting work here came out, Eric Van's group from Chile too.
Yeah.
Well, let's, we've had a couple of questions on biodiversity. Greg Hayes' question earlier about, how do we balance sequestering carbon on rangelands with the conservation of the species that require poor soils? How does biodiversity contribute to carbon sequestration across natural lands in California? So what is the role of biodiversity in carbon storage? I'll open it up to anybody, maybe starting with you, Asmeret, if you wish.
Yeah, so I personally don't see biodiversity and carbon sequestration as competing goals. I think they're complementary goals that we should strive for, and both also important in their own right. I wonder if maybe I misunderstood this question a bit, because when we're thinking about restoring health of soil to what it used to be, I feel like it's probably less of an issue to think about specific vegetation that is now thriving in a highly degraded soil, because on the balance, you really want to think about the potential, the multiple other issues associated with degradation of the soil beyond just one unique species, perhaps. But maybe if the person who asked this question is thinking perhaps of specific types of soils, right? There are these unique soils that are generally really nutrient poor, for example, soils that develop on serpentine were the first things that came to my mind. So those are very unique soils, very poor nutrient-wise soils, poorly developed in somewhat, that also are habitats to very unique species. So in that case, I wouldn't necessarily strive for making sure that we're applying tons of compost and changing that system to the point where we're compromising those native ecosystems that specific soil is supporting. So perhaps the way to go about is think about restoring certain lands that were degraded significantly from a multiple benefit perspective, co-benefits. One of them is going to be carbon sequestration, but if there are good arguments for unique ecosystems that should be conserved for their own sake, then I don't think we necessarily have to adopt these strategies across the board in a way that doesn't take account of unique ecosystems. Does that make sense?
Yeah, it does. Hey, Matthew or Patty, importance of biodiversity, species that require relatively nutrient poor soils to survive. Any thoughts?
I would definitely agree with Asmeret. What Asmeret was saying is I wouldn't advocate for applying compost to these nutrient poor, fragile, very specific ecosystems. And a lot of the work that's been done has been in the more typical type of rangelands in California that are extremely invaded, have exotic species already. And there has been studies coming out of Wendy Silver's lab at Berkeley showing that applying compost to those types of ecosystems does not, increase the exotic invasions or significantly change species composition or species richness in those already invaded ecosystems. So I would definitely recommend not disturbing the fragile native low nutrient soils.
So we'll go back to you, Matthew. Maybe we're going to take a 30-second lightning round. So we'll start with you, Asmeret, in a minute. So I'm giving you fair warning, but I'll run down the panel. Matthew, any thoughts on biodiversity?
Yeah, I mean, I think when we think about California forests, we know the forests we have today are not the forests we had 100, 150 years ago. So in some sense, the questions become, what types of forests do we want? What types of species do we want in these forests? What is our baselines? What are we restoring to? And so in that sense, I think it begins to, what are the actions you take at what scale and how that affects the local biodiversity as you transition or restore these forests. That's not to say that we all know there are many controversies surrounding endangered species and some disagreement that exists on what is the best path forward in these forests. But across a raft of studies, it tends to indicate most species are quite resilient to fire, and moving back to these more native or natural fire regime would be beneficial for the ecosystem.
Okay. So I've got my phone here, 30 seconds.
Okay.
Best opportunity, Asmeret. Give us a take-home message for the audience.
In my opinion, I think the best opportunity lies in adapting climate-smart land management practices across the board with the goal of restoring degraded lands, in particular with grazing land management and cropland management practices. That's where I think I would think is the largest benefit in terms of not just how much carbon sequestered, but also the large area that they could be adopted across.
Okay. Patty?
Yeah, I would definitely agree with Asmeret. There's a lot of potential for improving the sustainability of our agricultural lands and our rangelands that are not just going to reduce greenhouse gases, but also increase soil water holding capacity, increase agricultural productivity, and there's a lot of potential there. But I'd also just really like to come back to wetlands too, because of all the, not just the extreme carbon sequestration ability of those systems, but their co-benefits that they provide. Sea level rises is exponentially increasing. We're going to be grappling with that a lot in the Bay Area and in the Delta in particular. So it's a really high priority area, I believe, for California.
Great. Matthew?
Yeah, so I'm going to use maybe the analogy of closing the loop. There's a lot of agricultural residue, a lot of agricultural waste. There's going to be a lot of forest waste, but for a lot of forest biomass available, especially if we have ambitious goals to reduce fire risk. So I think the opportunities we have there are to get some, negative emissions, depending on how we utilize this, possibly create jobs and boost our economy, depending on what types of investments we want to make in the short run. And they may be expensive at the beginning, but they may pay long dividends.
Well, fantastic. An hour is not enough, but we are at the end of our hour. We didn't get to environmental justice issues. We didn't get to the effect of COVID on managing lands. We didn't get to negative emissions, as you just mentioned, Matthew. We had a question from Evelyn Loya at SoCalGas about negative solutions, and expertise in the national labs here in California in that space. So much to do too. I know CCST will be doing more in this space, so we can look for additional events and programs in that area. I'm thankful for the panelists, Matthew, Patty, and Asmeret, for joining us. I'm thankful for the audience and questions, and really appreciate everybody's time and thoughts. And stay safe. And I'll turn it over to you, Amber, if you have any final thoughts that you'd like to give us. But take care, everyone.
Thank you so much, Rob, and thank you to our wonderful panelists. Thanks to all of you who have joined us for this important conversation. We do want to keep it going, so please go to our website. You can get the contact information from our experts who you can connect with. I want to thank my team who put this together, in particular, Dr. Teresa Feo, who led the effort here. We have a fantastic team, and we also have a fantastic set of institutional partners. You heard mention of a lot of their work today. And we're really proud to be able to bring this science to inform the work that you're doing. So thanks, everybody.